Like I said, yesterday we talked about average rate of change, which was the slope between 2 points. Today we're going to talk about instantaneous rate of change, which is the slope at a single moment in time. The learning target here says students will use the limit definition of a derivative of a function to find derivatives. When you're finding a derivative, you are finding the instantaneous rate of change. Okay, so if I say find the derivative, I'm asking you for the slope at 1 moment in time. Okay. When I say find the derivative, I'm asking you for the slope at 1 point. Okay, that's what I want to know. What is happening? What is the rate of change at that 1 point? That's what a derivative is. The verb is to differentiate. So if I say find the derivative, that's the same thing as differentiate this function. Okay? Derivative, differentiate. You can see they kind of sound similar. Okay? Says derivative. It finds the slope of the tangent line to the curve at any point. So if I have a curve like this, and I want to know the instantaneous rate of change at this point, what I need to find is the slope of the tangent line. Okay, hopefully you remember what a tangent line looks like from geometry. A tangent line just comes up and it just like kisses that point and then keeps going. So it's going to come up and just kiss that 1 point, right, and then walk away, right? And then keep going, right? That's what a tangent line looks like. Okay. So what I'm finding when I'm finding the derivative is the slope of the tangent line. Okay, it's the instantaneous rate of change at that point. Okay, some common symbols used with differentiation. We have these three, which I call nouns. So the derivative is f prime. The derivative is dy over dx. The derivative is y prime. These are all ways to write the derivative. dy over dx is the change in y over the change in x, which, if I'm finding the change in y over the change in x, that's slope, right? y2 minus y1 over x2 minus x1. Okay, that's saying just that's the slope, right? I wrote that backwards. Change in y over change in x. Okay. I just realized I wrote change in x over change in x. Okay, this is a verb. This is telling you to find the derivative of your function. Okay, that's an actual operation. It's saying find the derivative of your function. Okay, but they all represent derivatives. The limit definition of a derivative, we previewed this last class. Okay. Provided that the limit exists, this is the limit definition that we're going to use to find the instantaneous rate of change. Another way you could write it, if you don't like delta x, some people look at delta x and they're like, oh, I'm not used to seeing that symbol. If you want to write that delta x is h instead, you can. Okay, it's the same thing, it's just calling delta x h, so you don't have to write delta x every time. Okay, so you can see it's the same definition, it's just everywhere we saw delta x before, they're replacing it with h, just because some people are more comfortable with that. Okay, so you just choose whatever you're most comfortable with. I'm going to be working with the delta x's. So like I said, if you want to plug in a different variable instead, that's fine. Okay. All right, find the derivatives with respect to the appropriate variable for the following function. Okay, so it says find f prime. What is f prime? The derivative. That's what it wants, the instantaneous rate of change. Okay, so I'm going to use this limit definition. Limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That's the derivative definition. Okay. So I'm going to look at these in chunks. First of all, I need to know what this chunk means. What does it mean if I'm finding f of, I'm going to write it over here, f of x plus delta x? What does that mean? Well, I know that f of x is 5x minus 4. So what's going to happen? Instead of plugging in x for x, now what am I inputting for x? x plus delta x, right? If I were to ask you what is f of 2, you would write 5 times 2 minus 4, right? So I just want f of x plus delta x. Bless you. Everywhere I see an x in this original equation, I'm going to replace it with x plus delta x. So it would be like 5 x plus delta x minus 4. This is just a side note. So that's what I'm going to replace first. We're going to have the limit as delta x approaches 0 of, what did I just say? 5 x plus delta x minus 4. Right, that's the first chunk. Then I have a minus sign, and then I have this function f of x. What am I going to put in for f of x? Well, f of x is just 5x minus 4. You do need to put this in parentheses, okay? If you don't remember to put it in parentheses, you're going to get the wrong answer. So you might want to put a little star here, bless you, and say you need to remember the parentheses, okay? All over delta x. So now I'm just going to start multiplying things out. We want to multiply things out in the numerator and combine like terms. So I get the limit as delta x approaches 0 of, this would be 5x plus 5 delta x minus 4, and then distribute the negative through, minus 5x plus 4, all over delta x. Any questions about that so far? Okay. Now, you should expect that things start cleaning up nicely. We have 5x minus 5x. Those are going to go away, right? Combine like terms. Negative 4 and positive 4. Those go away, right, when we combine like terms. So now I'm just left with this limit as delta x approaches 0 of 5 delta x over delta x. And what happens? Delta x is canceled. Okay, so that's nice. So now all I have left is the limit as delta x approaches 0 of 5. What is the limit of a constant? Just a constant, right? Is there anywhere to plug in 0 anymore? No, there's nowhere to plug in 0. So your answer here is just 5. Any questions about that? Yeah. So you have, this is just like if you had 5x over x, right? Because delta x is just a variable. So anything divided by itself is just going to give you 1. So 5 times 1 would be 5. Now 5 delta x minus delta x, that would be 4 delta x. Yeah. Okay. Now I want you to think about this. What were we finding when we're finding the derivative? We're finding the slope of the tangent line, right? So think about what this graph looks like. The graph's 5x minus 4. 1, 2, 3, 4. It has a slope of 5. 1, 2, 3, 4, 5 over 1. So here's my line. And what were we finding? We were finding the slope of the tangent line, right? I don't care which point you choose. Let's say I choose this point. What is the instantaneous rate of change at that point? 5. Let's say I chose this point. What is the instantaneous rate of change at that point? What is the slope of the tangent line? 5, right? See how for a line, it doesn't really matter what point you pick on the line. The instantaneous rate of change at any one of those points is going to be 5. Okay? That works for all lines. Anytime you have a linear equation, it doesn't matter what point you pick on the line. The slope of the tangent line is always going to be the same as the slope of the whole line. So, as a note. Okay, what does y prime mean? derivative, right? It's a noun. Find what? Find the derivative, the noun, derivative. Okay? So I'm going to use 2 over x for this example. So again, we have our limit definition of a derivative. We have f of x plus delta x minus f of x over delta x. Okay? So in this case, my function is 2 over x. So what is my x plus delta x? If I were to plug in x plus delta x in place of x, we would have 2 over x plus delta x. Does everyone agree? If I plug in x plus delta x for x, we would have 2 over x plus delta x. Okay, so that's what I'm going to put over here. We've got the limit as delta x approaches 0. And then look at this in chunks. I write my first chunk, f of x plus delta x. We said that it's this guy. Right? So I'm going to write that first. 2 over x plus delta x. Then we have a minus sign. Then I just have my second chunk as my function. So what was my function? My function was 2 over x. And don't forget this part, that it's all over delta x. Okay, you've got to remember that denominator. Okay. So now, the method that I like to use here is the least common multiple method. I don't like working with fractions, so the faster I can clear out the fractions, the better. Okay. If you want, you could look at getting a common denominator in the numerator. You could multiply this guy. You can multiply this guy by x over x, and this guy by x plus delta x over x plus delta x. You get a common denominator, put them together, and then copy, change, flip, right? Multiply by the reciprocal. But I just think that's harder to spend the whole entire problem working with fractions. This is my personal opinion. Okay? So what I'm going to do instead is I'm going to multiply the entire thing by the least common multiple. Which what I do is I look at the denominators, and I determine that the least common multiple is x times x plus delta x. So that's what I'm going to multiply the numerator and denominator by, is the least common multiple. When I multiply the first term by my least common multiple, what would cancel? X plus delta x's would cancel, right? And it would just leave me with 2x. When I multiply the second term by the least common multiple, what would cancel? The x's would cancel. Does everyone see that? So I would have minus 2x plus delta x all over. Okay. And when I multiply the bottom by the least common multiple, we would have x, delta x, and x plus delta x. You could write the delta x first if you wanted to. Okay, I just visually like it better to have x and then delta x. Just so we don't have x and x right next to each other. Okay, and we're still finding the limit as delta x equals 0. Any questions about how I jumped from that first step that's shown to that second step that's shown? Is that okay? Multiply by the least common multiple? Okay, now true or false. This is where I see so many mistakes all the time. True or false? Can I do this? No. There is a subtraction sign here. The numerator is not in factored form. Okay, so don't cancel right now. Okay, don't cancel right now. Put like a big star next to that part and put don't cancel. Because I see that mistake all the time where people will want to just and start canceling stuff. No, you have to multiply out the numerator first and combine like terms. Okay? Always multiply out the numerator and combine like terms before any cancellation. So that's what we're going to do. Limit as delta x approaches 0. We have 2x. Now look how nice this is. See how we're going to get a minus 2x Hello. And if I distribute this -2 through, we get -2 delta x. I do not multiply out my denominator. The denominator, just leave it in factored form. X, delta x, x plus delta x. Don't make more work for yourself. Okay, just leave the denominator factored. And multiply out the numerator, combine like terms. Don't multiply out the denominator. So you can see once I get rid of the 2x minus 2x, what else is going to cancel? The delta x's are going to end up canceling, right? Alright, so then I'm going to have the limit as delta x approaches 0 of what's left? The -2 up top, and the bottom we have x, and then x plus delta x. Okay, so I get this expression as simplified as possible, and then what is my last step of my limit problem? Once I have rewritten the function, then I plug in. Okay, so now that I've rewritten the function, now I'm going to plug in that delta x is 0. So we would end up with -2 over x times x plus 0, which is what? -2 over what? X squared. Great. X plus 0 is still x. I see people all the time that will say, look at this x plus 0 and say it's 0. I don't know why. Okay, x plus 0 is still x. So when I multiply x by x, I get x squared. Okay, so -2 over x squared. Remember, we're finding the slope of the tangent line. What this means is that at different x values, slope of the tangent line will be different. Okay. This is what do we start with? 2 over x, a rational function. So depending on where you're choosing x, the slope of the tangent line is going to be different. It's not like it's linear where the slope is going to be constant throughout. It's going to change. Okay, so like if you give me an x value of 3, at an x value of 3, the slope of the tangent line would be -2 over 9. Okay, so it's going to change depending on what x is. All right. Okay, we're finding the derivative of g of x. So same kind of deal here. We're still using that same limit formula. I'm not going to keep rewriting it over and over again. Okay, but the first one is f of x plus delta x, or in this case, g of x plus delta x. So what's it going to look like if I replace x with x plus delta x? Well, it's going to look like x plus delta x cubed plus 2. Everyone agree with that? That's the first part of my limit expression. I'm going to have x plus delta x cubed plus 2. Okay. Then I'm going to do minus g of x, and I'm putting all of g of x in parentheses. Okay. What is minus g of x? G of x is x cubed plus 2 all over delta x. Any questions about how I set up my limit? Okay. Now you could multiply this all out, or this is one of the rules I had written on the board. A plus b cubed. We had a property for a plus b cubed. We actually use Pascal's triangle. That's going to be a cubed plus 3 a squared b. Oh man, I'm going to run out of room. Let me write it somewhere else. Goodbye. I'm going to write it, let's do the top. A plus b cubed. Here's your property. A cubed plus 3a squared b plus 3ab squared plus b cubed. Now you might be thinking, man, Mrs. G has a good memory. She can remember all these properties. Okay, it's because I look for patterns. Okay, this is actually a property derived off Pascal's triangle. Look at how for the A's it goes 3, 2, 1, and there's no A. Okay, and for the B's, see how it starts with no B, and then we have B to the first, B to the second, B to the third. Okay, so I just look at how the exponents almost like flip-flop. One descends and one grows. Okay, and then there's 2 leading coefficients of 3 in the middle. Okay? I just look at that pattern, and that helps me remember it. Okay, so let's use that pattern. Okay, everywhere I see an A, here I'm going to replace it with X. And everywhere I see a B in that pattern, I'm going to replace it with delta X. Okay, so that's what I'm doing. I'm using that formula to get low. All right, so what do we have? We've got x cubed plus 3x squared b, which b is delta x, plus 3a, which is x, b squared, which is delta x squared, plus b cubed. So that would be delta x cubed. Right? And that's just the first part. Then you have plus 2. And I'm going to distribute the negative through. So we get minus x cubed minus 2. Goodness gracious. And that's all over delta x. Okay, now it looks awful, but we know that things are going to get better and stuff's going to start canceling. Right? We can actually start to do it right now. What cancels? The x cubed will cancel, right, when we combine like terms. And the 2's will cancel, plus 2 minus 2. Oh, I worked this first. Hold on a second. Okay. Okay, so go ahead and write out what's left in a separate line. While I get up a new smart notebook. Oh, I'm moving stuff now. Okay. So we have the limit as delta x approaches 0 of, so we got 3x squared delta x plus 3x. I want you to understand that delta x is one quantity. Okay, so you're really squaring one quantity. But if you don't want to write the parentheses in around delta x every time, I'm okay with that. I'll know that you mean implied parentheses. Okay, so I'm just going to write delta x squared, but really delta x is one quantity, right, that's being squared, plus delta x cubed all over delta x. Any ideas about where to go from here? I'm not sure of an idea. Okay, so if there was multiplication here and here, then I could just cancel these. Okay, but because there's not multiplication, it's addition. What I would actually have to look at doing is when you have addition, you have to divide every term in the numerator by delta x. So you divide the first term by delta x, you divide the second term by delta x, and the third. So every single term gets divided by delta x. Okay, you can look at it that way. That works because every term does have delta x in it. So you would just divide every term in the numerator by delta x. Another way you can look at doing it is factoring out a delta x. And then once you have factored out a GCF of delta x, then you can cancel one for one. Okay, so until you factor, you can't cancel 1 for 1. You would have to divide out a delta x in every term. Okay, good idea though. Yeah, we want to go ahead and simplify this as much as possible, so I will want to divide out a delta x. Okay, so I'm going to just show this where I factor out the delta x in the numerator, just a GCF. Okay, so this is what I would have left inside of the parentheses after I factor out a delta x. Okay. And see how now I have multiplication here? Once I have 2 factors being multiplied together, then I can cancel 1 for 1. Okay. All right, and then this is what I have left, 3x squared plus 3x delta x plus delta x squared. At this point, now I can plug in 0 for my delta x's. So I would end up with 3x squared plus 3x delta x, which is now 0, plus delta x squared, which is now 0. So what am I going to end up with? Just 3x squared. So like I said, these problems look awful when you start them, but you should know that things are going to simplify and cancel nicely. Okay, it's going to be like, ah, it's a huge problem. And then you're like, yes, but I know everything's going to cancel out. It's going to be great. Okay? Any questions on that? The more of these you do, guys, it's going to feel more systematic. Okay, it looks like a lot right now, but I promise if you do a lot of these, it'll feel very systematic. So I'm going to do the same thing on the last problem. I'm going to start by plugging in x plus delta x for x. So I have x plus delta x plus 1. That's for my first part. Then I write my minus sign. Then I just have my regular function all over delta x. Now, I see a limit problem with radicals in the binomial. What analytical method are you going to use to evaluate that limit? I heard it. Conjugates, right? Whenever you are evaluating a limit problem analytically, and you have a binomial with a radical, you should immediately be thinking conjugates. Okay, so I'm going to start this problem by multiplying the top by the conjugate. So the conjugate, instead of having a minus sign separating it, will have an addition sign separating the 2 radicals. And don't forget about the denominator. You've got to multiply the denominator by the conjugate as well. Okay, like I said, it's got to look awful before it gets better. Okay, now what's the nice thing about multiplying conjugates? Do you have to completely FOIL it out? No, you know the middle terms of conjugates are going to cancel. So in the numerator where I'm multiplying conjugates, my first times first, the radical is just going to go away, right? And then I do last times last, and the radical is just going to go away, which is really nice. So even though it looks awful, just multiply by the conjugate, and it'll actually come out pretty nice for us. So first times first, we get x plus delta x plus 1. Because we're squaring a square root, so those are inverse operations, so they just go away. And then I have minus. And what needs to follow a minus sign? Parentheses. Don't forget your parentheses. After the minus sign, if you don't put your parentheses, then you're going to not experience all that nice cancellation. Okay? Last times last, you just get x plus 1 inside the parentheses. Okay. All over this hideous denominator, which, like I said, don't spend time multiplying it out. Just leave a factor. We have delta x, and then we have our conjugate. There's x plus delta x plus 1 plus square root of x plus 1. Just like that. Now, can I cancel, true or false, can I cancel these delta x's right now? No. There's addition, right? You need to completely multiply out the numerator and combine like terms and factor before you can cancel anything. So I'm going to distribute the negative through. delta x plus 1 minus x minus 1. Ooh, that looks nice, doesn't it? Delta x. See, I love these problems because I can take something awful and make it look so much better at the end. It gives me great satisfaction to simplify things. Okay. So now you can see that the x minus x's, when you add those together, would go away. And the plus 1 minus 1, when you combine those like terms, you get 0. And look at what's left up top. Now it's just the delta x. And what do you see down below? Hey, a delta x. See why we left the denominator factor? Because then now that goes away. So what's left in the numerator? 1. Okay, there's still something left in the numerator. It's not like your fraction just goes away. You still have a fraction here. So make sure you're still writing this as a fraction. 1 over this awful conjugate. Ew. Okay, so now that I've reduced everything, right, I've simplified this fraction as much as I possibly can. Now I'm going to go ahead and plug in 0. Where do I plug in 0? Delta x. Okay, so this is going to be 0, and that's really it. Okay. So I'm going to end up 1 over, this would just end up being x plus 1 underneath the radical, and then this will be another x plus 1. So if I have one of the radical x plus 1s and then another one of the radical x plus 1s, how many radical x plus 1s do I have? 2. Okay, so I have 1 over 2. Square root of x plus 1. Now, if you can get to that point, you get full credit for the problem. I'm like, yes. Not the best answer because there's a square root in the denominator. The best answer would be the rationalized form, where I multiply top and bottom by the square root of x plus 1. Okay, so this would be the best answer, the rationalized answer. But if you can get to this answer, I will be happy. Okay. Any questions? You can see it's pretty systematic. Once you get the original limit written correctly, the rest is just a lot of algebra. Okay. So, all right, I'm going to give you about 20 minutes to work here, maybe like 25 minutes. You are working on this 2.1 number 2 worksheet. And I'll go ahead and post the solutions just so that you know if you're doing them correctly. If you want to work with a partner, you're welcome to do that. Okay? Please ask me questions. That's why I'm giving you class time to practice these.